A motor control center becomes cost-effective or practical when certain criteria are met. Firstly, consider the number of motors. An MCC is often a good choice when multiple motors, typically 5 or more, need to be controlled from a central location. Secondly, think about space constraints. Individual motor starters can occupy too much space on the floor or in a panel board, and a MCC provides a more compact solution. Thirdly, maintenance and accessibility are important. MCC provide easy access to motor starters and other devices, making maintenance and troubleshooting more efficient. Fourthly, safety and code compliance are key. MCC meet electrical codes and provide protection features such as circuit breakers or fuses, which are often required for industrial applications. Fifthly, scalability and flexibility matter. MCC can be easily expanded or modified as additional motors or control devices are required. Other factors to consider include power requirements. MCC can handle higher amperage loads than individual motor starters. Control capabilities are also relevant. MCC can provide complex control functionality such as interlocking, sequencing, and remote monitoring. Cost savings are a major consideration. While MCC have a higher initial cost, they can reduce long-term maintenance and operating expenses compared to individual motor starters. Reliability is crucial. MCC are designed for industrial applications and offer higher reliability than individual motor starters. Aesthetics are a plus. MCC provide a clean and organized appearance in electrical rooms or industrial settings. As a general rule, if the number of motors exceeds 5 to 7 and space is limited, an MCC becomes more cost-effective and practical. However, the specific requirements and circumstances of each project should be considered to determine the optimal solution. To elaborate further, let's delve into the technical advantages of utilizing a motor control center in scenarios with multiple motors. When dealing with numerous motors, typically 5 or more, the centralized nature of an MCC offers significant benefits in terms of wiring and installation. Instead of running individual power and control cables to each motor starter located separately, an MCC allows for a consolidated wiring approach. All power feeds and control signals are routed to the MCC, simplifying the overall wiring architecture and reducing the amount of cabling required. This not only saves on material costs but also reduces installation time and labor. Furthermore, the centralized location of the motor starters within the MCC facilitates easier troubleshooting and maintenance. Technicians can quickly access and inspect multiple starters from a single point, rather than having to locate and access individual starters scattered throughout the facility. This streamlined access reduces downtime and improves the efficiency of maintenance operations. Regarding space constraints, individual motor starters can consume a considerable amount of floor space, particularly in applications with a large number of motors. Panel boards filled with individual starters can also be bulky and difficult to manage. An MCC, on the other hand, offers a compact and space-saving solution by housing multiple starters in a single, organized enclosure. This is especially beneficial in facilities where space is limited or where maximizing floor space is crucial. The modular design of MCC also allows for efficient space utilization, as additional starter units can be easily added or removed as needed. In terms of maintenance and accessibility, MCC are designed to facilitate easy access to the motor starters and other components. Starters are typically mounted on pull-out units or swing-out panels, allowing technicians to quickly inspect and service them without having to disconnect or remove any wiring. The MCC also provides convenient access to control wiring, terminals, and other components, making troubleshooting and repairs more efficient. Moreover, MCC often incorporate diagnostic features and monitoring systems that provide real-time information about the status of the motors and starters. This allows technicians to quickly identify potential problems and take corrective action before they lead to equipment failures or downtime. From a safety and code compliance perspective, MCC are designed to meet stringent electrical codes and safety standards. They incorporate various protection features, such as circuit breakers, fuses, and overload relays to protect the motors and starters from damage due to overcurrents, short circuits, and other electrical faults. The MCC enclosure also provides a barrier against accidental contact with live electrical components, reducing the risk of electrical shock. Additionally, MCC often includes safety interlocks that prevent unauthorized access to the equipment and ensure that the system is de-energized before maintenance or repairs are performed. Scalability and flexibility are also key advantages of MCC. The modular design allows for easy expansion or modification as the needs of the facility change. Additional starter units can be added to accommodate new motors, or existing units can be reconfigured to meet different control requirements. The MCC can also be easily integrated with other control systems, such as programmable logic controllers or distributed control systems, to provide advanced automation and monitoring capabilities. This flexibility makes MCC a cost-effective solution for facilities that anticipate future growth or changes in their motor control needs. Power requirements are another important consideration when evaluating the suitability of an MCC. MCC are designed to handle higher amperage loads than individual motor starters, making them well suited for applications with large motors or high power demand. The MCC typically includes a main incoming power disconnect that provides a central point for disconnecting power to the entire system. This simplifies the process of de-energizing the equipment for maintenance or repairs. The MCC also distributes power to the individual motor starters through a busbar system, which provides a reliable and efficient means of power distribution. Control capabilities are also enhanced with an MCC. MCC can provide complex control functionalities such as interlocking, sequencing, and remote monitoring. Interlocking prevents certain motors from starting or stopping unless other motors are in a specific state, ensuring safe and coordinated operation of the system. Sequencing allows motors to be started or stopped in a predetermined order, optimizing the performance of the process. Remote monitoring enables operators to monitor the status of the motors and starters from a central location, providing real-time visibility into the operation of the system. In terms of cost savings, while MCC have a higher initial cost than individual motor starters, they can reduce long-term maintenance and operating expenses. The centralized nature of the MCC simplifies maintenance and troubleshooting, reducing downtime and labor costs. The improved reliability of MCC also minimizes the risk of equipment failures, reducing repair costs and lost production. Additionally, the energy efficiency features of MCC, such as variable frequency drivers and soft starters, can help reduce energy consumption and lower utility bills. The enhanced reliability of MCC is a significant advantage in industrial applications. MCC are designed to withstand the harsh environmental conditions typically found in industrial facilities, such as temperature extremes, humidity, dust, and vibration. The robust construction of the MCC and its components ensures reliable operation over a long period of time. The use of high-quality materials and components also minimizes the risk of failures and extends the lifespan of the equipment. Finally, the aesthetic appeal of MCC should not be overlooked. MCC provide a clean and organized appearance in electrical rooms or industrial settings. The modular design and standardized components create a professional and well-maintained look. This can improve the overall image of the facility and contribute to a more positive work environment. In conclusion, the decision of whether to use a motor control center depends on a variety of factors, including the number of motors, space constraints, maintenance requirements, safety considerations, scalability needs, power requirements, control capabilities, cost savings potential, and reliability expectations. By carefully evaluating these factors, you can determine whether an MCC is the most cost-effective and practical solution for your specific application. Let's consider some specific scenarios where a motor control center would be particularly advantageous. Firstly, in a large manufacturing plant with dozens of motors powering various pieces of equipment, an MCC would provide a centralized and organized way to control and protect all of these motors. The MCC would simplify wiring, reduce space requirements, and improve maintenance access. Secondly, in a wastewater treatment plant, where multiple pumps, blowers, and mixers are used to process wastewater, an MCC would provide a reliable and efficient way to control and monitor these devices. The MCC could also incorporate advanced control features such as automatic pump sequencing and alarm annunciation. Thirdly, in a commercial building, where multiple HVAC units, fans, and pumps are used to regulate the temperature and airflow, an MCC would provide a compact and cost-effective way to control these systems. The MCC could also integrate with the building automation system to provide remote monitoring and control capabilities. Conversely, there are also situations where individual motor starters may be a more appropriate choice. For example, in a small workshop with only a few motors, the cost and complexity of an MCC may not be justified. Individual motor starters would be a simpler and more economical solution. Similarly, in a remote location where space is not a constraint, individual motor starters may be easier to install and maintain. In addition to the factors discussed above, there are also some technical considerations that may influence the decision of whether to use an MCC. For example, the voltage and current ratings of the motors, the type of motor control required, and the environmental conditions in which the equipment will be installed should all be taken into account. Furthermore, it is important to consult with qualified electrical engineers and contractors to ensure that the MCC or individual motor starters are properly sized, installed, and maintained. Proper installation and maintenance are essential to ensure the safe and reliable operation of the equipment. Now let's discuss some of the components typically found in a motor control center. The main components include the incoming line section, which provides the main power connection to the MCC, the busbar system, which distributes power to the various motor starters, the motor starter units, which control the individual motors, the control wiring, which carries the control signals, and the protective devices, which protect the motors and starters from electrical faults. The incoming line section typically includes a main circuit breaker or fuse disconnect switch, which provides overcurrent protection and a means of disconnecting power to the entire MCC. The busbar system is typically made of copper or aluminum and is designed to carry the full load current of the MCC. The motor starter units typically include a contactor, an overload relay, and a circuit breaker or fuses. The contactor is an electromechanical switch that connects and disconnects power to the motor. The overload relay protects the motor from damage due to overloads. The circuit breaker or fuses provide overcurrent protection for the motor starter unit. The control wiring carries the control signals from the control system to the motor starter units. The protective devices, such as surge suppressors and ground fault relays, protect the motors and starters from electrical faults. It's also important to understand the different types of motor starters that can be used in an MCC. The most common types include across-the-line starters, reduced voltage starters, and variable frequency drives. Across-the-line starters apply full voltage to the motor at startup, providing the highest starting torque, but also drawing the highest starting current. Reduced voltage starters reduce the voltage applied to the motor during startup, reducing the starting current but also reducing the starting torque. Variable frequency drives allow for precise control of the motor speed and torque, providing energy savings and improved performance. The choice of motor starter depends on the specific application requirements. For example, across-the-line starters are typically used for small motors that do not require precise speed control. Reduced voltage starters are typically used for larger motors that require reduced starting current. Variable frequency drives are typically used for applications that require precise speed control and energy savings. In addition to the components and types of motor starters, it's also important to consider the various features and options that are available for MCC. These include things like communication interfaces, metering and monitoring systems, and advanced control functions. Communication interfaces allow the MCC to be connected to a control system, such as a programmable logic controller or a distributed control system. Metering and monitoring systems provide real-time information about the status of the motors and starters, such as voltage, current, power, and temperature. Advanced control functions include things like automatic pump sequencing, alarm annunciation, and energy management. The choice of features and options depends on the specific application requirements and the level of automation desired. Finally, it's important to emphasize the importance of safety when working with MCC. MCC contain high-voltage electrical components and should only be serviced by qualified personnel. Always de-energize the MCC before performing any maintenance or repairs. Use proper personal protective equipment, such as gloves and safety glasses. Follow all safety procedures and guidelines. By following these safety precautions, you can minimize the risk of electrical shock and other hazards. When selecting an MCC, it's essential to consider not just the initial cost but also the life cycle cost. Life cycle cost includes the initial purchase price, installation costs, maintenance costs, operating costs, and disposal costs. A higher initial cost MCC may have lower life cycle costs due to reduced maintenance, improved energy efficiency, and longer lifespan. Therefore, a thorough life cycle cost analysis is crucial for making an informed decision. Furthermore, the environmental impact of the MCC should also be considered. Choose MCC that are energy efficient and use environmentally friendly materials. Consider the recyclability of the MCC components at the end of its life. By choosing environmentally responsible MCC, you can minimize your carbon footprint and contribute to a more sustainable future. Before making a final decision, it's advisable to visit several MCC manufacturers and inspect their products firsthand. This will allow you to assess the quality of the construction, the ease of maintenance, and the availability of spare parts. Talk to the manufacturer's representatives and ask them questions about their products and services. Get references from other customers and contact them to learn about their experiences with the MCC. By doing your due diligence, you can ensure that you are selecting the best MCC for your specific needs. Once the MCC is installed, it's important to establish a regular maintenance program. This program should include periodic inspections, cleaning, lubrication, and testing. Keep accurate records of all maintenance activities. Train your personnel on the proper operation and maintenance of the MCC. By implementing a proactive maintenance program, you can extend the life of the MCC and minimize the risk of unexpected failures. In addition to regular maintenance, it's also important to have a contingency plan in place in case of a failure. This plan should include procedures for identifying the cause of the failure, isolating the affected equipment, and restoring power as quickly as possible. Keep a stock of spare parts on hand to minimize downtime. Train your personnel on the implementation of the contingency plan. By having a well-defined contingency plan, you can minimize the impact of a failure on your operations. In conclusion, the decision of whether to use a motor control center is a complex one that depends on a variety of factors. By carefully considering these factors, you can make an informed decision that will optimize your motor control system and improve your overall operations. This detailed exploration provides a comprehensive understanding of when a motor control center becomes a cost-effective and practical solution, covering various aspects from technical advantages to safety considerations and life cycle costs.